and talking in the afternoons, I realized that we mention a lot numerical relativity, but it's sort of the thing no one talks about. So I changed the title so that we can have a little more time on the basics of numerical relativity. Now, there's no way in 30 minutes that I'm going to give a school on numerical relativity, nor do you want me to, I promise. But I thought I'd better back up a little bit so people understand what's the difference between numerical relativity and post-Newtonian theory, and how is it used when we do gravitational wave, hopefully astronomy. So I wish I had a picture of Satya dancing last night, but I don't. Someone get me one. Okay, so here is what we keep talking about, right? This is a gravitational waveform. You're going to see a couple funny things that are different than what you've seen in the past. First, it's truncated a little funny right here. And that's something we want to talk about, the fact that when we do numerical relativity, we begin in a moment in time without the history of what's happened before. The other thing is this weird unit here. So right now, I could be doing supermassive black holes or stellar mass binary black hole collisions. It doesn't matter. It scales with mass. So until we actually interact with the detector, we don't have to make a choice about what our mass scale is for binary black holes. That's not true for binary neutron stars or black hole neutron star numerical relativity, because they have an intrinsic scale that comes along with the matter. So here's the picture that I stole from the University of Syracuse, just so I didn't put the picture Ajith showed that we always show when we talk about binary black holes from Kip. So this is a picture of sort of like a time series of two compact objects, well, black holes, pretty sure, merging. Here's the merger and ring down. So as we go to the left back in time, post-Newtonian is more and more an accurate approximation to Einstein's equations of general relativity, and it breaks down when those black holes are moving too quickly and when their finite extent becomes more important. We can't treat them like point masses. And as you go to the right, as Ajith was just talking about, we can do perturbations of a Kerr space-time and get the ring down. So numerical relativity could, in principle, keep going to the left, but I'll explain how that slows us down, and it's very hard. But we get ring down pretty much for free. So we don't actually have to glue on perturbation signals to numerical relativity signals, although to get the full time history, we do glue on post-Newtonian. So let's see if this works. Oops. All right, I thought I'd really start with the basics. I promise not to go too deep, though. So this is Einstein Equation, right? It's so pretty, so simple, and it's so complicated. And we even make the right-hand side 0. So we're going to do vacuum binary black holes. It's really just G mu equals 0, but we're not making any approximations whatsoever. So the largest error we have in numerical relativity is that we're going to do a discretized version of this equation, so we have something called truncation error. It just comes from the fact that if we could make our resolution down to 0, we would recover the continuum solution. So we're going to solve the full nonlinear Einstein equation. Our errors, as I said, arise from that truncation error. We have to make decisions. The problem with general relativity is that we are given too much freedom, right? So we have a lot of choices we make that can influence the quality of our answer, and we have to do things like extract the gravitational radiation. So we're actually solving for the 4D space-time. This is why this equation is the hardest that I know of in physics, because we don't have the fun of electromagnetism where we're given an arena in which our gravitational waves are propagating, or in that case, are electromagnetic. So we have to solve the space-time and the gravitational radiation. The gravitational radiation is part of that space-time. So what we're going to do, one choice, is take a three-dimensional spatial chunks, label it with our metric G. You can think of it as a 3x3 matrix if you want. And it's time derivative, because we're going to solve partial differential equations, so we have to specify initial data, just like you would do in a wave equation. So we're going to take these 3D chunks, and we're going to evolve them at each instant of time. So there's two main flavors of numerical relativity codes. One of them is called Einstein Toolkit. And most people in the numerical relativity business use some variant of the Einstein Toolkit, although I don't know anyone who uses it pure right out of the box. So careful if you just download it and hope for the best. And the other big code is SPEC, which is the spectral code. Anyway, mostly run out of Caltech, Cornell, and a few other places. So I'm not going to do a review of numerical relativity, so I include a few references for people to go back and look at it, because it's just not viable in a half hour. So here's my cartoon of initial data for numerical relativity. What we're going to do is we're going to take one instant of time in this history of a coalescing black hole, and we're going to use that information motivated by post-Newtonian dynamics at that time to specify our initial data at t equals 0. And when we say initial data, we have to specify those two quantities, the metric and its time derivative in that moment of time and one step back. So here's what it looks like, right? This is a cute cartoon, but in reality, we have to take these two black holes, we have to give them individual masses, individual spins and orientations. We have to maybe try to force the eccentricity to be 0, so we have a nice quasi-circular orbit, and we have to do some kind of separation. So this is typical, just like you would do in like Kepler's law. But we have to satisfy 4 Einstein constraints, and it gets much more complicated to get that initial data at the end of the day. So that's what we do to do numerical relativity. And then once we've done this, one solution, one choice for these parameters takes days to weeks to months, depending on what we're after. So that's the problem. So the reason why everybody at this conference who's talked about binary black holes and how they model the numerical relativity waveform, it's because it takes so long just to get one solution from this. And that means we don't have a functional form. John?
What's the size of the mesh in space?
Depends. So I have a picture of that. Is that next? Yes, okay. Good job, John, okay.
That wasn't a plant.
Could be a plant. I should hand you, no. So it depends on a lot. So this is the mesh that John was asking about. So when we do these things, there's different meshes depending if you use the spec code or the Einstein Toolkit type of code, but I'll describe this one, which is what we use, which is a finite differencing situation. So the problem we have is that we have to take that 3D big chunk of space at one instant of time, and we put a big grid on it. So if you just take a slice of that space, that's what this is, a 2D slice of that space, think of it as a big mesh, almost like a strainer if you're going to strain pasta or something. And very far away from the black holes, we have a very coarse mesh, so only thick pasta will fit in that one. And as you get in towards the black holes, we get a very, very, very fine mesh. And the reason we have to do that is because we have to, you see this thing here? This is the Homer Simpson. Anyone see I'm getting so old, no one knows the Simpsons anymore. And I'm in Brazil. But they did this really good 3D Simpson where they actually pretty accurately, show the stretching of the grid as it gets closer to the black hole. And that's the problem. So space-time is stretching, right? Because a black hole is making everything infinitely dense and horrible. So we have to actually resolve that. So we have to put a lot of points across the region where the black holes are, say a minimum of 50 points across each. If I make one of those black holes much smaller, then I have to put more points across. So it's going to cost me more time and resources. And then I have to also resolve the gravitational wave as far away from those black holes as possible, because gravitational radiation is defined in general relativity as outgoing gravitational waves at spatial and temporal infinity. We don't have infinity in a box, so we have to make other decisions to get that radiation closer, and we have to resolve it. So any radiative process is hard because you have to resolve that, that radiation. So that points can be like 1m per, like if you wanted to have a sine wave and you wanted to resolve a period, you need at least 3 points or more across that period. So that will determine how much resolution we have out here. So that's the tension. We have to do both of those at once. The more mass ratio you include, the more clock time, human time per time step it will take. The higher you spin the black holes, the more human time per time step. The time steps get smaller. Everything gets worse. The further apart those two black holes are, which would mean the more orbits we'd have, the more gravitational wave cycles we would recover from numerical relativity, the more time it takes. And it's doubled, right? So not only is our grid bigger, so we have to do a bigger spatial slice, the black holes are moving slower. So it takes even longer as you move forward in time. So all those things are the reason why we're not churning out tons of numerical relativity waveforms. Did that answer your question? It's hard for me to say exactly the points because it depends on what we've chosen. But so this is what gravitational radiation looks like. This is along a particular line of sight, right? We reduce the information when we look at it like this. This is what the output looks like. This is I think AEI's picture, I forgot to write it down. So this is their two black holes with some radiation is happening, and we extract that radiation as far away as possible on a sphere. So really it looks like some function of time at some radius theta and phi. And then we use, spin weighted minus 2, spherical harmonics, it doesn't matter. Spherical harmonics that map theta and phi to L and M. And then we start talking about the waveform we're used to looking at, which is the dominant quadrupole. Yeah, Niels? We extracted at a finite radius. We extracted at a finite radius because we need enough resolution. So if we went too far away, it wouldn't be high, the resolution would be too low, we wouldn't get a good waveform. You can use there's some people who use interesting coordinate systems, but we just extrapolate it to infinity because we understand how it falls off. But there hasn't been much difference. One thing I should note, since we just talked about that, is that luckily there are more than one approach. So we have done a lot of comparisons of our answers among the different groups. Quite a bit of them, actually, in Ninja and NRAR. I didn't mention it here because I didn't mean this to be a review. So we're pretty confident because we've done a lot of high-order comparisons between codes. Yes, sir? Sure. So there's no good boundary condition. Is the problem. So what is your boundary condition? Your boundary condition is everything should be going out and nothing should be coming in. So when we do this, we just make sure that we push our outer boundary far enough away that any reflections don't have time to come back and contaminate our waveform. The spec code can't get away with that. They use co-rotating, so they have to be more careful. So they choose a more sophisticated enforcing that everything's outgoing at the boundary. But that's basically the physicalness of it. Yes, really far away, yeah. And you have to resolve it enough that you don't end up having mesh refinement reflections coming back and getting you. So even though in some sense, we can do these binary black holes, you can go download the code if you want yourself, I don't recommend you do it on your own at home. Like, call us, let us help you. It's an art form a little bit. And the reason why it's an art form is mesh refinement is hard. And so it's very finicky, and I know very few people who are really gifted at doing it. I'm not, right? So I'm not the best at running numeric relativity waveforms. Some people, it's almost like experimental. They can just be gifted at how many waveforms they can produce. All right, so we recover this waveform as a function of time for some series of L's and M's. And the 2-2 mode, because we're an n-spiraling gravitational radiation, L equals 2 will always be our first one and our most dominant, usually. And then we have M equals 2 is usually our dominant. So this solution, but in numerical relativity, we get all the other modes to some degree of accuracy, depending on how large they are. But this is the strongest, so usually this is what we're showing you. The solution here with this M, if we want to put some units on it, if we wanted to scale to a 100 solar mass system, say 250 solar mass black holes, then the rule of thumb is for every solar mass, you add about 5 microseconds. So this whole 2,000 units of M time would be about 1 second. So if you remember what Salvador was showing us this morning, that was many more seconds. So this is the very last part. Of course, it depends on what mass it is, clearly. More questions about that? This one gets messy. I should have probably cleaned it up more. So given that it takes a while, but we kind of know what we're doing. I say kind of because we don't routinely do super high spins that are Kerr limited, although there are 2 papers that have explored really high spins. The reason for that is the choice of initial data we make sometimes makes that challenging. And we've done some extreme mass ratios. Our group has Q equals 15. I think we have a Q equals 20 actually as well. And RIT has a Q equal 100, but routinely those aren't done because they take forever because those black holes are so slow out there. So this is the space coverage of just the Georgia Tech where I am, how many waveforms per spot we have on this space. This is the non-processing. We'll talk about that again. We heard about it this morning. This is our processing catalog of waveforms. The spec collaboration has 171. We have about 600. There's more in other groups around the world. I just showed you this so you can see. So you can see here these gaps. So what we're doing is we make a choice of those initial parameters, and then we run the code. We get that one waveform. So I have here in the bottom on a couple different slides questions that I think is important for numerical relativity to think about as we go forward in gravitational wave astronomy. One of them is how can we speed up the waveform production? And the other is understanding how do we figure out where these holes cause problems for gravitational wave data analysis and when it wouldn't really matter. So we want to choose our next and our waveform smarter. Right now we just do it by, I feel like doing this parameter. I mean, there's no real reason that we're doing it. Well, we don't have them on a website like SXS does. You can just call us. We'll give you waveforms. But I know I have to build a website and do that. It's not that easy, apparently. Laziness. I know, my poor grad student. My poor grad student just got involved in a search in LIGO, so he's not coming up for air anytime soon. Okay. So what does this look like? We hear about this a lot. This is my cartoon version of what we keep talking about. Now, when I said in my original title that I was going to work on intermediate mass black holes, that meant in my head greater than 40 solar masses. And what it really meant in my head is you can't ignore merger like we did this morning. So more like what Ajit was talking about. So of course, every community has these different definitions of these masses. So here is really hard to see because I highlighted it in gray. That was brilliant of me. But these is a post-Newtonian waveform in blue, believe it or not, and a pink NR waveform. And the idea here is depending on the total mass of that binary black hole, we're going to the merger frequency will either sit within the band or not, or how much of it will sit in the band. So if we were binary neutron stars, you already saw, are really low mass, you can ignore the merger completely, do it with post-Newtonian, happy, happy. Well, not me, but these guys are happy. So if I'm at about 20 solar masses, this is a total guess. These cycles don't correspond to that. It's just a cartoon. But if I were at 20 solar masses and I took a Fourier transform of that h of t we were looking at, it would look something like this blue line. And the part of it, just, some part of that merger would come in, but you would need a lot of cycles early on. If I'm at 100 solar masses, that merger has started to hit right where LIGO is very sensitive. And so that merger now is sitting right in the sweet spot of LIGO. And you need fewer cycles that aren't numerical relativity. So the tension here that you might have, I think we've been alluding to during this week, is that post-Newtonian is getting worse as we go towards merger, but numerical relativity struggles because it takes so long to add cycles at that further separation. So if we shorten the numerical relativity time, we get more waveforms per parameter, but we have larger errors in our waveforms depending on the mass coming from the breakdown of post-Newtonian. So that's the tension. We can do really long waveforms, but then you'll only get a few. Which one's better? I don't know. I need the data people to tell me. So what is the longest waveform ever produced? This is from, they call themselves the SXS collaboration, but it's the spec code people. They did, I heard a rumor that it was an accident. They did a 350 gravitational wave cycle. I think it took over a year to do. It's beautiful. Yeah. I mean, it starts out slow and then it speeds up at the end, but yeah, painful, right? So this is a Q equals 7. They had a really hard time with merger, so they actually ended up having to do that several times and map on to other simulations, but that doesn't matter because the point here was to really test post-Newtonian, right, and EOB-NR. So they use this. EOB-NR is built from fitting to numerical relativity waveforms, and this gives you so many cycles to really test whether or not the post-Newtonian and the EOB is doing a good job. And it was, right? So I think up until about 25 cycles before merger, it was a very, very good match in terms of phase error. So that just tells us that 25 cycles is still a lot of cycles, and depends on what your physical parameters are, but this is the longest waveform ever created from numerical relativity. So this is really hard to see. Maybe I shouldn't use my cute iPad to do these things anymore. But anyway, what this plot is from the paper I swear is coming out with all the waveforms from my graduate student Kron. This is the number of simulations we have versus how many cycles we have, what solar mass could you inject it into advanced LIGO or advanced Virgo, starting at 30 hertz, which is a little high, and what total mass we would have. So in other words, this would be with no post-Newtonian cycles added. And so we go from about 50 solar masses, which is what that is. That's like the lowest total mass you can inject a bunch of our waveforms without adding post-Newtonian. So here you could, this thing covers much longer and much lower mass. But the number of cycles increase dramatically as you try to lower that total mass. So it gets very tricky. So that was just for fun. So we can do it, but it's hard. And so it turns out, not surprisingly, that we probably need, depending on the accuracy of that, so LIGO Virgo people have to tell us, I need this much accuracy, and then we can say, I can give you those waveforms or not. Because the problem is that you really don't want us, I think, to spend over a year on every numerical relativity waveform to get that many cycles. So it's always going to be a collaboration between the two groups. So how do we use these waveforms? One, we use them as, I call it God, but it's inappropriate, nature. So we use NR waveforms as the true solution. If Einstein's equation is the true solution of gravity, you can inject it into the detector, or you can test your search pipelines. That's what Ninja did. What NR, AR, and a lot of other groups do is model. So you use numerical relativity waveforms, and you take your semi-analytic models that Ajit and others have talked about, and you fit. So you have a functional form of the physical parameters and get out a waveform, which we don't have in numerical relativity, right? We have discrete waveforms like that plot I showed you. The biggest models are EOBNR, which we've heard about, and FEM, which you also heard about. I added this, which was cheeky of me. This is one we're working on, which is principal components. But it's basically more for model selection. So here's kind of the way it goes. We produce an NR waveform after making a decision about physical parameters. These people model, stick it into their model, test their fits. Someone has to build a template bank to actually do the detection. This can take so long that there are people who do reduced order models of the EOBNR model in order to produce that template bank. And then you do the search. So it's not only is NR hard, but of course data analysis is also hard and computationally time consuming. So one of my concerns is, how do we speed up the lag time between we've produced a new numerical relativity waveform? None of these guys have even used our 600 processing waveforms, right? So the lag time between those and actually creating these models and templates. So I would say that the models are working hard, and Ajit and others could tell you, to include processing, spins, and all these other things, but it's a lot of work, and they're moving forward, but it's a challenge. So as this total mass increases, the effect of spins, procession, higher modes, all of that becomes more pronounced than it is, I think, for lower mass, as we heard this morning. So now it gets crazy, because I try to show you too much, sorry. So spin can be anything. This is a problem. We don't have really strict statements on what our spin alignment or anything should be for these larger mass systems. So we have to kind of evolve all of it. It's a really large parameter space. Here's an example of what we're dealing with. Ajit already talked about the energetics of the system. So we're going to start out with some angular momentum here of the system, orbital angular momentum. The total angular momentum is the spins plus that. And at the end of the day, as Ajit said, we have a mass and some spin. So usually, even in procession, right? Everyone knows what procession is. It means your orbital plane is moving and your spin vectors are moving. Even in procession, most people still expect the models that you won't get this huge difference between the initial and final J, that they'll be more or less aligned. And so one of the goals of numerical relativity, in my opinion, is to not only solve the next waveform, but also pick out places where our assumptions break down so we can test how many signals we might miss if some of these exist in nature, or know how to look for them if they do pop up. So here's a typical procession case. It means that things are going to work out as we expect. And this cone is showing you what the one spin as it's evolving in time. The green is tracking the change in the orbital angular momentum, and the blue is that other spin. And what we see here is that our initial and final orbital angular momentum, total angular momentum, more or less point in the same direction because things average. What happens, it's really hard to see these, I know, here. What happens when you have a crazy system? So this system is kind of fine-tuned to you have no spin in one of the black holes and spin in the other. So the yellow vector is gone. That was one of the spins. And in this case, this is what the orbital angular momentum is doing. And here's where our change in J happened. So we get a 9 degrees change in J. Not too big, but it still happens sometimes, depending on your initial parameters of your system. So if I take those two cases, the typical precession and this sort of crazy one, I get 8% energy radiated in typical. Notice the crazy precession doesn't radiate much, which means it'll be harder to find, right? That SNR is going to go down. The final spin magnitudes, one is 0.24 and one's 0.7. It's hard to get a final spin 0. You can do it, but you have to fine tune. And the angle can be up to 9 degrees. In fact, the angle between initial and final can be up to 30. That's the biggest we found. So we've talked about that, testing things to see. So that's part of the fun. You can see normally they're within 30 degrees, but we need to figure out whether or not the search pipelines or models are going to be able to, that will be a problem or not for them. Another fun thing is, just because it was mentioned earlier, is inclination. It seems kind of romantic to think of these precessing orbital guys to be doing this as it goes through LIGO, but that's not really true, right? The timescales are really fast. That precession timescale is slower. But in our most dramatic case, we did have an inclination from the time it would have entered the band till it merged of 90 degrees. So that was the craziest run we had in terms of how much that orbital plane would have moved. And it took a little bit of a strange spin situation, one lining 90 degrees from Z, and the other non-spinning. So that was my example of the craziness that can happen. And I'm sure you'll yell at me if I should shut up. But so the other thing underneath all these waveforms we produce is these higher modes, or subdominant harmonics, as they're sometimes called, that I mentioned earlier. So part of the problem is that when we look at, this is such a pretty big number. When we look at this picture, it's pretty good, of a binary, and when we think of the 2-2 mode, the quadrupole mode being dominant, we're assuming that that binary is face on to LIGO. So if LIGO is on the floor, the binary is sitting like this. Now if there's precession or unequal, that starts to not be completely true anymore, but anyway, that's what we're assuming. And so what's happening is, as we have precession waveforms, the energy is being removed from the 2-2. It's sort of being put in all these other modes, which means that we're not capturing all the energy in the system when we only focus on 2-2. Here's the difference between non-precessing, non-spinning, a Q equals 7, whether you look at it face on or you look at it slightly inclined, if the binary was in a different location. And there you can see the difference between face on. You wouldn't have detected difference between H2 and all of the full H, but at a random orientation, you see how much different that full waveform would look like at a theta phi location. So these are more like cautionary tales. We just want to understand how important this will be when you add a detector. Now, it will depend on the detector. If we're talking Einstein telescope or LISA, the SNR can get so high, as Matt and I were talking about earlier. If you want to subtract out the signal, you'd have to recover all this information very accurately. So it depends on which detector we're in. So what does numerical relativity tell us? Yeah, it gives us the solution, in some cases painfully. It will do things like really modeling, not even modeling, solving Einstein's equation for precession. It gives us the higher modes, but only when we combine it with the gravitational wave data analysis and parameter estimation will we know when these things are important, when it makes an impact. I actually was trying to put up a Jeeth's papers plot, but it wouldn't let me. It was too big or something. It was kind of funny. But there's a couple recent papers, mine's a little bit older, by Jeeth and Bonanno's group, where they look also at these higher modes, for instance, to see what their impact would be on the detector. So if you take a system that's large, this is 0, but this is 200 solar masses, so it's way more important for high mass systems, and you look at how far away you could detect these black holes, depending on their mass ratio, 1 to Q equals 4, whether you had all the modes, the dark lines, or you had only the 2-2, the dashed lines, you see a common theme. We agree with it. These guys agree with it. As your mass ratio increases, and as your black holes get more massive, you start losing information if you ignore the higher modes. That will happen with precession. It's really hard to see in my plots. That's just terrible. What not to do in a talk is part of this process. Here, I'll make it big. So in this example that we show, just to give you a feel, energy radiated, aligned spins are always the biggest bang for our buck. Equal mass aligned spins give us the most energy radiated. And then depending on their mass ratio, precession next, and then here's unequal. So all of this is important. We're going to detect these. This is just to show that if you don't have all the modes, you start getting these discrepancies about how far away you might see that signal. But it's not something to worry about with lower mass binaries. So that's an example of what we can do. And then what I thought I would do for POW is questions of interest. Now this is to me, but some of the things I'd like to think about, and maybe some of you have something to say about it. So one of my worries is how to speed up NR waveform production. This is hard, right? So what could we do? We could decrease the accuracy. You guys could turn around and say, you know what, if we're going to look at more massive black holes where we need more information about precession, we don't need the small phase errors because we don't have as many gravitational wave cycles to sum up. So why don't you guys reduce the accuracy, go here. That's going to be limited by the systematic errors in the detector. It's something we've been talking about in what I call Camp B in the basement. No, it's first floor. And obviously the limit placed on by astrophysical needs. We could also find ways, this is crazy now, crazy land, but the only other numerical relativist in the room is Pablo, so he won't tell on me, hopefully, is to find ways to reduce the complexity of the equations. And in my brain, I literally mean like zeroing out terms, because they're hard to compute, and that would speed us up. It would no longer be a correct solution to Einstein's equation, but maybe we can find an intermediary between post-Newtonian and numerical relativity. Let's see. I can imagine this working for highly separated black holes, like in between the point where post-Newtonian breaks down and we pick back up. And something I already mentioned, if you can't do any of this, we could at least do a smart choice of the next NR simulation so each one counts maximally. One way that my group's exploring that is using machine learning methods to try to get the person out of it to see if we can work on the impact each run has on the models that are being produced. And that requirement has to be defined by the data analysis. Yes? Yes. I think our mesh refinement could be better. So the Einstein Toolkit people all use pretty much, there's one group who doesn't, but all use pretty much carpet. And I don't know if it's really the best thing ever. There's nothing else out there, so someone would have to write a new one. I don't have anyone better. Do you, Pablo? But it's only adaptive as it can be because we have to get that radiation coming out. So it's not like what some people can do. Pablo even tried finite elements once, if I remember, but do you know of anything better? It'd be better. You would never recover though, like if you really if you really have to have 50 gravitational wave cycles from us, factor of 2 isn't going to cut it, in my opinion. That's where I think you have to get a little crazy. But on the other ones, I agree. I would love a new mesh refinement. That would be great for Christmas, if anyone. We do, not everyone does. But the differences there haven't, it's not like one group's going really fast and the others aren't. So none of that's making such a huge impact. They follow the black holes. And that's one of the reasons that we have these patches that follow around the black holes. The spec group has these spherical ball-and-ball type patches. But they don't follow the black holes. They have everything co-rotate. So it's a completely different type of mindset. But anyone has more ideas, that's fine. I'll take your mesh refinement if it will work. More?
Cosmology, there are many groups that have different adaptive mesh refinement that are more sophisticated, but you don't have to have such a high degree of accuracy when you discretize the operators. So in order to get the waveforms that they were showing, we had to have 6-order accurate.
Oh yeah, I didn't mention that.
And that means that's one of the things that finite difference control.
Nasty. Yeah, at the end of the day, we are solving Einstein's equations for a black hole. And there's no way around that. So it is challenging in ways that other communities haven't had to deal with, I think, a little bit. So the last couple of things that I thought were of interest, as I mentioned this one already, how you speed up the time between new and our waveforms, other than mine making the waveforms public, that would probably help, and templates. And, you know, can we, I think a lot of our intuition about what these numerical relativity waveforms should look like or what type of parameter accuracy we have is coming from lower mass compact binaries. And I think Ricardo said and other people have said it hasn't been explored as much for higher mass, so maybe we could work together a little closer and figure out if we could reduce some of this in the NR side. And it would be nice to really have it be, and I don't know if this is possible right now, maybe you guys could tell me that if you have a model, if just a few more waveforms, how they can get added to it, or if you really have to start kind of over with the fitting procedure. I don't really understand how each new additional piece of information could be quickly fitted into these models. And then this is just for fun. Actually, I really think you were talking about this a little bit in the end, which is when you start, instead of doing kind of the parameter estimation, which we think of typically, instead doing kind of model selection. I think this is very interesting also in the cases of a higher mass system, whether or not it's processing or not, and if whether we can approach the modeling a little bit differently, which is one of the reasons why our group is exploring principal components directly of the numerical relativity to see if we can do something a little less beautiful as the lower mass stuff, but maybe faster. Thank you. Take this off.
So you've done a very nice job. So we have 10 minutes of questions.
Yes, Ricardo.
You know, the ultra long waveform, 350
Yeah. I did know. I think they keep it to being less than 0.25 radians. They lose that at, I want to say 25 cycles out, but I find that I remember both being 25 suspicious, but something like that. So they found that EOBNR and the numerical relativity matched up to a high phase.
Yeah, but the systematic numerical relativity error.
So what does that mean? I mean, I've always thought it meant to you, what is the error in the phase?
Yeah.
So yes, they have that. So that's like less than a radian. I think it's 0.25 radians or something.
And it's basically increasing?
It basically increases, and at the point where it deviates from that is a number of cycles away from merger. Let's call it about 25. And that's when they found that they started deviating too much.
But the estimation of this error is independent of the SOBNR comparison.
Yes. Right. We can always tell you how our phase error is accumulating as we go in time, and then it's up to you to tell us this is the point where it's going to cause a problem, right? But we have that information. Yeah, and we can go get that paper. I have it written down. I just don't remember off the top of my head. Yes, sir.
There is a recent work where template managers were generated by using a very small number of numerical.
Right, Duncan Brown and
Kumar.
uh-huh. Yeah, I usually include that. I didn't do this one. Yeah.
Yeah, so all I was going to say was maybe that is what can speed up the numerical relativity simulations. They work backwards.
Yeah.
What they did was they use a bunch of numerical
Mhm.
forms to say what parameter space you can cover. Instead, you can ask the reverse question.
Yeah.
Okay, I want to cover this parameter space. Where do I need to?
Yeah, I agree.
In fact, you mentioned PCA. That's the other way.
Yeah.
So both of these methods, I would imagine, should reduce your computational requirement by an extra factor of 1,000.
Yes, I daydream about that.
Forward by looking at that result. I had hardly 15 pages.
Yeah. It just gets silly.
They all need to be locked. The reason why this happens is numerical relativity simulations don't care about mass, total mass, right?
Mm-hmm.
That drops off. There's only really one-dimensional lens. If you're worried about only aligned spin waveforms, which is what we currently do for simulations.
But I don't do those. I think those were done. I mean, maybe not completely. A good question to ask, I think, in numerical relativity would be, from that type of thing, if you made a template bank of aligned spins with a bunch of Qs, other than having like Q equals 50 or 100, which is not easy to do you really need any more aligned spin waveforms? And I'm not sure.
Probably not.
My gut would be no, but.
So that's the reason why I keep going back to this question of, can we have please at least about half a dozen waveforms that can verify that TOV is correct?
Yeah, but that's SXS job.
Because
I don't do that.
can we make the biggest impact?
Yeah.
The biggest impact, although everybody's excited about spins and precision and whatnot, but we fundamentally have an ignorance here because we don't know whether there is going to be any impact.
Yeah, I guess the reason why, I mean, I assume that the Caltech Cornell CETA group is better at that than we are. So I feel like it's their job. Maybe they're slower than you'd like to be. Granted, it would take us a year of our full allocation to do one of those runs.
I would say,
No, but that's not my job. You're talking to the wrong person, right? I do well merger. And I know you love your binary neutron stars. And I fully support that. So that's why I talk about the higher masses. Because it's just, then I should use a spectral code. I don't think you want these finite difference in codes to doing the comparison with. But Pablo might disagree with me.
No. What do you mean by testing if EOB is correct? Let me show you.
not EOB. Yeah, EOB. Okay.
So EOB has this parameter that gets fixed by numerical relativity simulation. So if I pick one of the waveforms from numerical relativity that was used to fix those parameters, EOB is going to match with that. So what will be a good test for EOB?
It won't be because you will be dynamics. You may fix the parameters or coefficients, whatever you want, with some calibration, but it has to stay in phase over of the order of 1,000 cycles. And that's not good to do. You know, any of I don't want that 1,000 cycle waveform to be used for calibration. You calibrate the wave, your EOB by using shorter waveforms, maybe 20, 30 cycles. But then you want to ask the question whether it is going to stay in phase, that is EOB and not stay in phase over about 1,000 cycles.
So why isn't Post-Newtonian good enough to do it way out there at 1,000 cycles?
And EOB don't agree all the time.
Oh, so you want someone to decide.
Yes,
Sorry?
I mean, I don't see the need for those 1,000 cycle check. I mean, we know that there post-Newtonian physics is under control, all post-Newtonian approximate agree. I mean,
They don't necessarily, not for all purposes. If you want to measure equation of state of neutron stars,
No, of course,
or if you want to do
Yeah.
some other very subtle test,
Yeah.
you absolutely have to have control over the phasing over 1,000.
yeah, but not over 1,000 cycles. Those effects are more important to
There are cumulative effects even in the
Don't panic.
the tidal
We'll still see him.
They don't start up. And we also know that parameter estimation gets better measured at lower frequencies. But because we observe the system again and again and again.
Stanley, if you go back in time from ring down to post-Newtonian, I think in the part in which numerical relativity operates, EOB, they're going to just match because by construction, that's how EOB is.
But Satya wants us to go further back.
EOB is defined by its own dynamics. EOB is defined by its own dynamics. There's an Hamiltonian, you start with Hamiltonian, and you write down the equations of motion, and from that you construct the waveform. It's determined by its own dynamics.
Well, no, it's fit to NR as Pablo's one.
Determines the dynamics.
Well, they do fit a bunch of parameters to numerical relativity. They're not doing EOB, they're doing EOB and R. So they've contaminated their beautiful Hamiltonian with some nasty NR fitting. Yeah.
They don't fix everything else. Anyway, this is becoming very
We have Camp B for this, darlings. Oh, we do have time.
Portion of the waveform.
Yeah, of course. Yes. That's how you make EOB.
No,
But I still understand what he's saying. I do have the loudest voice. I understand what he's saying, though, because it's still true that
and I'm not defending EOB.
they're going beyond that. Ha ha ha.